Good morning, everyone. Today we are excited to present our project title, Analyzing IoT Network Traffic for Security Insights. This work was carried out by our team including Phạm Bá Việt, Nguyễn Văn Tuệ, Bế Thành Tiến, Phạm Huy Thành, Nguyễn Sơn Hải, and Phạm Quang Triệu. We were supervised by Professor Trần Hùng from the .com lab. Let's begin with the objective of our project. Our main goal was to analyze real IoT network traffic using Python. Through this, we aim to identify anomalies, understand protocol behavior, and detect potential security threats. We visualize the result through Power BI dashboard, and through this process, we gain hands-on experience in data analysis, cybersecurity threat detection, and security reporting.
Like, let's talk about our methodology. We divide our approach into several stages. One, data analysis. Two, visualization with Power BI. Three, advanced challenge. Now, start with the data analysis. After gathering raw IoT network traffic data, our very first and most important step were cleaning and extracting the data. Why was it so crucial? Because if you push CapEx in, you get CapEx out. Poor quality data lead to unreally reliable results. Here, what we remove: one, corrupted records, things like malformed data packets. Two is complete entries, missing critical information like timestamp or port numbers. Three, irrelevant data field that was useful for our analysis. Then we attracted key features including shows and destinations IP address, port numbers, network protocols like TCP, UDP, and ICMP, packet size, and timestamp. The clean data became the foundations for all our visualizations and machine learning models. Skipping this step would have made our entire analysis unreliable. uh, Next, uh, without clean data query, we move to processing, preparing the data for our models. We focus on four main stacks. One, normalizing numerical values. For example, scaling packet size to a standard range. Two, encoding uh, categorical data, like converting protocol name to number, TCP equals 6 and UDP equal 17. Three, handling missing value using techniques like median substitution. For parsing out datasets to prevent peers toward more common attack try. This careful preparations is where our machine learning model could learn effectively and our visualizations would show true pattern, not the data quiz. Next. Now let's look at what we learned from analyzing the security behavior. We examine which port were targeted most, like port uh, 53 for TNS attack. Unusual packet size that might indicate TTOS attempt. Traffic pattern over time like sub pieces by 3 a.m. Uh, out Alkifying TCP protocol 6 were most often used in attacks like SYN flow, while UTP protocol 17 were more used for normal traffic. The insight directly help us set pattern detections, uh, results, and select more important features for our machine learning model.
Now let's take a look at the summary of the IoT traffic data we work with. To begin, we analyze how often each type of activities appear in the dataset. These include normal traffic as well as several kinds of attacks such as DDoS, MITM, and more. We focused on two key metrics. First is the count, which simply tells us how many times each type of traffic occurs, and the second one is the percentage, which shows us what portion of the total dataset each traffic type represents. This will give us a clear view of how the network traffic was distributed, whether it was mostly normal or dominated by malicious activities. Is one important first step in understanding the overall behavior of the network. Next, we wanted to understand how the attack types related to specific network protocols. We create a cross-tabulation or table comparing common protocols like TCP, UDP, or ICMP with each attack label. This analysis will give us two valuable insights. Firstly, it will show us which protocols are commonly used by different types of attacks, and it also helps us to identify which protocols might be more vulnerable to specific threats. For example, if we notice that the DDoS attacks mostly use UDP, we could focus more on monitoring UDP traffic, and this step helps us to recognize the pattern in how attacks spread across the different protocols, which can be crucial for improving network security in the real-world IoT system.
Hello, and I will now talk about our data visualization in protocol distribution in IoT network. First, we have let's begin by examining the protocol distribution in the IoT network. As you can see from both the pie chart and tree map on the left, protocol 6, which correspond to TCP, which dominates the network traffic, making up approximately 85.8% of all communication. And we have protocol 17, or we can call it UDP, accounts for about 8.38%, and Protocol 0, typically used for reserve or testing purposes, making up roughly 5.81%. This suggests that most of the communication in the IoT environment is connected, oriented, and reliable, which is expected in use case requiring consistent data transmission, like device monitoring or system control. Moving on, we have our average packets per minute by hour. Now let's look at how traffic volume varies over time. The large number at the top, 39.53 billion packets per minute, represents the overall average across the dataset. If we look at the line chart on the right, we can see that packet activity peaks around 12 p.m., followed by a sharp drop after 1 p.m. The horizontal bar chart below shows a similar pattern. Between hour 9 and hour 12 have the highest level of traffic, while hour 10 and 15 are significantly lower. The waterfall chart on the bottom left also highlights a steady increase in traffic throughout the day, indicating consistent packet transmission growth until it hits the peak. From a security perspective, these traffic spikes might coincide with scheduled device communication or automated updates, but they could also indicate periods of vulnerability, which should be monitored more closely. And moving on, we will have traffic type analysis. Looking both the bar and donut charts, the most common type of traffic observed is port scan, accounting for nearly 36% of all traffic. This is followed by binning traffic at 26.7% and ICMP flood attacks at around 18.29%. Other types of malicious traffic like ping sweeps, DNS floods, and vulnerability scans are also present, though at a lower rates. Finally, the horizontal bar chart on the bottom gives a great comparative view, showing that binning traffic, while significant, is still outweighed by the total malicious attempts like scanning and flooding attacks. This indicates that the IoT network is under constant probing and attack, especially with scanning techniques aiming to identify vulnerabilities. Proactive monitoring and automated threat detection mechanisms are crucial to mitigate this risk. Now we will move to my part, which I did, which is advanced challenges. Our first is anomaly detection. Well, here's the code as you can see, and this anomaly detection was performed using the isolation forest algorithm, which identifies outliers in the network traffic data, key statistical features such as port numbers, packet lengths, and time were used. The model was trained to detect the top 1% of the abnormal patterns, labeling them as anomaly, while regular traffic was marked as normal. Here I will show you our visualized part of the data. On the x-axis, we have the mean packet length, especially the average size of packets over a period. And on the y-axis, we have the standard deviation of packet length, which tells us how much variation there is in packet size. So I will talk about how and why are these metrics are important. Well, under normal condition, packet size tend to stay relatively consistent, but when there's an anomaly like a DDoS attack or some form of exfiltration, the packet size and the variability often change dramatically. And here you can see the color coding, which has the color blue and then the color red. The blue dot represents normal traffic, and you will notice that they are concentrated in the lower left part of the plot, which means the packets are smaller on average and less variable. Red dots, on the other hand, represent anomalous traffic. These are scattered broadly across the plot and especially in higher ranges. For both mean and standard deviation, this pattern makes sense. Abnormal traffic often shows more erratic behavior, higher average sizes, and greater inconsistency, which is exactly what this visualization captures. And in summary, this plot is not just a pretty chart, it's a practical tool. It helps data scientists, network analysts, and security professional understand why and where anomaly occurs, and it's a step toward turning raw data into actionable insight. Thank you for listening to my part, and we will move on to our second part of advanced challenges, which is attack classification.
We also built an attack classification model using the random forest classifier. We use features like packet length, port number and time, and split the dataset into 80% training and 20% testing. We evaluate the model using the confusion matrix, which gives us insight into how accurate a model was at detecting attacks. On this slide, you can see the confusion matrix that summarizes a model classification result. This matrix gives us a clear picture of how well the model performs. Understanding this pattern is essential for cybersecurity. A false negative where an attack is missed would leave a system vulnerable, while a false positive might trigger unnecessary alarms. So the confusion matrix play a vital role in evaluating our system real-world reliability. To wrap up, we would like to thank you all for your attention and time. This project has been a great learning experience for us. We not only explore the behavior of IoT traffic, but also apply machine learning techniques to detect security threats in a meaningful and useful way. We learn how to process raw data, identify different kinds of attacks, and evaluate a model performance using tools like confusion matrix. We truly believe that the skill will help us in future research or work application related to cybersecurity. If you have any question or would like to discuss further, we would happy to answer. Thank you again.